Okay. All right. Thank you, everybody. I'm Rebecca Jensen Clem. I'm an assistant professor at UC Santa Cruz. And today I'm going to be talking about a range of new adaptive optics technologies that my group is developing to support exoplanet imaging and AO-fed science broadly at Keck 2. Now, the Keck AO system has played a critical role in the history of high contrast imaging, as Christian Marois' group used Keck to take one of the earliest images of another solar system. That's the HR 8799 4-planet system that's shown here. And since those early days, the most directly imaged planets that have been discovered since then have been discovered by extreme AO systems like GPI and SPHERE. But Keck has continued to play a critical role in following up those discoveries at longer wavelengths, such as the 2 L-band images that you see here, as well as with high-resolution spectroscopy. And in fact, we now have rotational velocity measurements for a number of directly imaged companions, thanks to Marta Bryan's near-SPOW observations, and now more recently KPIC observations that were published by Jason Wang just a couple of months ago. But where Keck and all AO systems, extreme or otherwise, have fallen short is our ability to directly image planets that have similar masses and periods to those in our own solar system. So the big challenge for the 2020s and beyond is to directly image planets that are closer to their host stars than what we've been able to do so far. And we know from radial velocity studies that such planets are abundant, and lower mass planets like Jupiter. And then with the next generation of 30-meter class telescopes, ice giants and rocky planets as well. So looking at this diagram, you might ask, why have we directly imaged so few planets so far? Why is this task so technically challenging? Well, the answer mostly lies in adaptive optics. If we consider the star and planet light collected by our telescope and entering our AO system, which I've shown a cartoon of here, the light first encounters a deformable mirror, which changes its shape to counteract the effects of atmospheric turbulence. And how do you know how to change the shape of your deformable mirror? Well, we pick off part of the light and we send it to a wavefront sensor. And on the basis of images from our wavefront sensor, we compute the next command for the deformable mirror. And if we're doing exoplanet imaging, we will often insert additional coronagraphic optics between the AO system and our science detector. So where do our AO systems fall short? What are the major sources of error in these systems? Well, first of all, there are only so many deforming elements on your deformable mirror. Currently, Keck 2 has 349 deforming elements, and Keck AO scientist Sam Ragland is leading us in an upgrade that would bring a 3,000 element deformable mirror to Keck 2, so we're looking forward to that future upgrade. But the next major source of error is the time lag between sensing and correcting for atmospheric turbulence. So for Keck 2's pyramid wavefront sensor, that time lag is 1.7 milliseconds. That may not sound like much, but it's plenty of time for the atmosphere to evolve and for our correction to become out of date. And no matter how fast your wavefront sensor detector readout time, and no matter how fast your computer is, you're always going to have some amount of time lag because you have to wait to collect photons on your wavefront sensing detector. So to address this pretty much inescapable time lag, my group has been pursuing a technique called predictive wavefront control, where we predict what shape we should put on the deformable mirror one time lag into the future. So how do we do this? Well, we consider if we could create some filter, F, that we would apply to a vector that contains our last few wavefront measurements. And we want to minimize, in a least squares sense, the distance between the result and what the true wavefront will look like one time lag delta t into the future. So we've set up a pretty straightforward least squares linear algebra problem here. We can take a set of training wavefront sensing measurements and use those in place of h and omega here to solve for the filter f. And this is a method that was originally proposed by Olivier Guillon and Jared Males a few years ago, in which they're also pursuing at the Keck AO system. So a few months ago, our team, led by UCSC postdoc Micah Van Coten, and in collaboration with the Keck AO team, had some opportunities to test our predictive control algorithm on Sky. So the way we approach this is we alternated between taking data with the standard controller that's used every night and then alternating that with predictive control. And then we made histograms, which is what you're seeing here, of the residual wavefront error. So here, smaller is better. We want to have less wavefront error in our AO system. And we found that on Sky, our predictive controller gave us about a 1.7 times improvement to our RMS wavefront sensor error. So we were very excited by that improvement, but because our group is particularly focused on high contrast imaging, we wanted an opportunity to try predictive control with the coronagraph in place. And that's exactly what we did at our next on-Sky opportunity. We used the L-band vector vortex coronagraph and we took images with NERC2. And we created a contrast curve. So this is telling you how much fainter of a planet compared to the star you could detect as a function of the planet's separation from the central star here in full width half maxima. And we found that the contrast is 2 to 3 times better with predictive control than with a standard controller when we focus on just this region very close to the star where we know most planets will be located. So we're very excited to repeat these results on many different nights and in the future offer this as a facilitized mode to other science users. So the next term in the adaptive optics error budget that I'd like to address comes from imperfections in the optics that occur between the wavefront sensor and the science camera. So usually we don't measure or correct for these types of aberrations. But the result of these aberrations are bright spots in our coronagraphic science image called speckles. And these can hide the signal of true planets. So in the sequence of GPI images, you can see many speckles, as well as the roiling residual atmospheric turbulence that our AO system didn't fully correct due to error terms like the time lag that I mentioned earlier. So I'd like to introduce you to a special type of coronagraph that we use to characterize these residual speckles so that we can go on to remove them with a deformable mirror. Now, most coronagraphs contain several different optics, and what I'm going to show you here is the second of the 2 optics in this coronagraphic system. So this optic, this coronagraph, blocks a great deal of the light, but it has a hole punched in the top of it. That's what's represented on the top of the screen, a pinhole punched in this mask. And so our first mask, which you don't see here, has attenuated much of the starlight. And then the starlight that it didn't attenuate, it pushed it up to the location of that pinhole. So we have much of the light going through that pinhole and going to our science camera. But of course, some starlight inevitably escapes that first mask and still continues to the camera unimpeded. So what do we see at our science camera with this funny setup of coronagraphic masks? Well, we see that speckle pattern as you did for the GPI images, but because we're interfering the starlight with itself, now we have interference fringes superimposed on top of that speckle pattern. And because the planet light was off axis, it missed most of this coronagraphic action and it proceeded straight to the science camera unfringed. So now, by processing these images, we can use this fringing data to understand what the wavefront aberrations were and go on to correct those with a deformable mirror. So this work, this type of coronagraph called FAST, has been spearheaded by UCSC postdoc Benjamin Girard, and he has set up a demonstration of this technique in the lab at Santa Cruz. We have a new high contrast lab setup called the Santa Cruz Extreme AO Lab. And here, this is a video of what he found. He put residual atmospheric turbulence on the deformable mirror and then used this fringed science image to extract information about those speckles and to go on to correct them with the deformable mirror. And so here in that left-hand image, you see him digging out that dark hole and revealing an exoplanet in our lab setting hidden underneath. And Ben is now working on a proposal to implement this technique as an optional mode for the pyramid wavefront sensor plate at Keck 2. Okay, so the last thing in this whirlwind tour of AO technology that I want to talk to you about considers the AO system in its broader context as part of the observatory. Now, the Keck primary mirror, like those of the coming generation of 30-meter class telescopes, is of course segmented. And most of the time, these segments are aligned perfectly well for any science application at Keck. But the exact alignment of these segments becomes important when you're dealing with extreme AO for high contrast imaging. So recently, as part of the KPIC project, a new wavefront sensor was installed in the Keck 2 AO system. And the goal of this wavefront sensor was to be able to monitor the relative positions of the primary mirror segments and to be able to update those in the future. So this type of wavefront sensor being commissioned by the group of people you see here is called a Zernike wavefront sensor. And the way it works is it introduces a little phase bump in the central lambda over d region of the focal plane. And when you go back into collimated space, you'll find that the intensity of an image that you form is related to those original wavefront aberrations. So I'm just going to give you a teaser of what we have found with our initial engineering data with the Zernike. So a couple months ago, we intentionally introduced some pistons. So we moved 3 different segments of the primary mirror by 200 nanometers. And then we took an image with our Zernike wavefront sensor detector, and we see exactly what we expect. The intensity of this image corresponds to the phase. So we very clearly see those segments that we pistoned. Okay, so I see I'm running a little bit short on time, so I'll just leave you with these next steps. And also with this pre-Delta Wave photo of the AO team at UC Santa Cruz. And I'm happy to take any questions. Thank you.
All right, thanks so much for the talk, Becky. Any questions in the room? We have one from Dimitri.
Hi, Becky. Great talk. So in your slide showing the residual histograms with the predictive controller and without, I just noticed that the tail seems to be heavily biased for the predictive controller. How do you explain that?
Yeah, that's right. So we've been examining that in a few different situations. Initially, we tried several different time lags that we assumed for the system. We tried assuming time lag of 1 millisecond and then 2 milliseconds. And we're finding that as we get closer to the true time lag of the system, that tail is less and less of a problem. So that's part of it. The other part is probably some remaining instabilities that we still need to work out for the predictive system.
All right, and we have a question on Zoom. It is, how are you approaching retraining the EOF basis throughout the night on Sky? And Becky, if you don't mind reminding us what EOF is.
Yeah, that's right. So EOF refers to this kind of linear algebra-based technique that we're using for predictive control. And yeah, so as for how often do we retrain, there are different ways you can do it. What we're moving towards is, can we retrain pretty much as often as we can? So as soon as you're done retraining one filter, you'll retrain the next. But what Micah Van Coten has also been working on is a method of recursive predictive control. So you're always improving your predictions. So we hope to be able to try that on Sky pretty soon as well.
All right, thank you, Becky. Any other questions in the room? Last chance for questions on Zoom or Slack. All right, let's give one last big round of applause to Becky.
Thank you.